Okay, hi guys, Miss Burns here. We're going to take a look at section 1.4, which is on a topic called complex numbers. So up until now, if you might have been asked at some point, what's the square root of a negative number? You would say there's no real solution, it can't be done. But somewhere along the line, mathematicians wanted to have a way to deal with negatives under a square root. And so they defined something called the imaginary number I, and I is defined as the square root of -1. If we square this equation, so I squared, if we square what's under a square root, remember that gets rid of the square root and just leaves you with what's under the square root. So when we work these problems, I want you to remember that I squared is always going to be replaced with -1. So let's look at an example here. If I just ask you for the square root of -81, think about that we could write that as -1 times 81. And there's a rule in algebra that says if you have a square root, you can break it up according to its product. So we could think of this as the square root of -1 times the square root of 81. And of course the square root of -1 we just said is I, and the square root of 81 is 9, so this just simplifies to 9i. Now you don't have to go through these steps every time necessarily. You could have just looked at it and said the square root of 81 is 9, there's a negative under the radical, so it's I, but I want you to see where all that comes from. The number I belongs to a larger set of real numbers, or I'm sorry, imaginary numbers that are called complex numbers. And complex numbers are all numbers that are in the form a plus bi, where a and b are real numbers. A lot of times we would say that a, we call that the real part because there's no I attached to it, and b we would call the imaginary part of the complex number. So we're going to do a few things in this section with performing operations on complex numbers. So here's a question where it says write the result in standard form. So we're looking at -5 plus 7i minus -11 minus 6i. So all we're going to do is we're going to treat this just like we would if this were an x. And we're essentially going to distribute the negative and combine like terms. So when you're adding and subtracting these complex numbers, you're just going to combine like terms. So this gives me -5 plus 11. Make sure you see where that's coming from. Negative and -11 made that a positive 11. And then the 6i also became positive, so we've got 7i plus 6i. So combine like terms and we get 6 plus 13i. Okay, this time they're asking us to multiply these two complex numbers together. So a complex number is a binomial. Remember, a binomial is just an expression that has two terms in it. So 2 minus I is a binomial, and 1 plus 3i is a binomial. So to multiply these out, we can treat them just like any other binomials that we're multiplying and use the FOIL method. So take a minute, pause it if you need to, but I want you to FOIL these terms out, just like you would if they were x's instead of i's, and write down on your paper what that would give you. And so you should get 2 for the first term, 6i for the outer term, -1i or -i for the inner term, and then -3i squared for the last term. Of course, the middle terms you're going to combine. Those are like terms. And remember earlier we said that I squared always gets replaced with -1. So we get 5i in the middle from combining like terms. And then the -3i squared, that's like -3 times a -1, which makes that +3. And then, of course, the 2 and the 3 could combine and leave us with 5 plus 5i. A term you want to be familiar with is the conjugate of a complex number. And so a conjugate is essentially where you take a binomial and the second term of the binomial you change the sign. So if the number is a plus bi, the conjugate would be a minus bi. So we're going to use that in a question like this, where they're asking us to divide these two complex numbers. So we have 7 plus 4i divided by 2 minus 5i. So the way we're going to handle this is we're going to multiply the numerator and the denominator by the complex conjugate of the denominator. So think about what the complex conjugate of 2 minus 5i would be. And that is 2 plus 5i. So we're going to multiply 2 plus 5i on the top and the bottom. We can do that because it's really like multiplying by 1, the same thing on the top and bottom. And I'm going to FOIL the numerator and FOIL the denominator. So again, take a minute, pause the video. I want you to write out on your paper what you would get if you FOILed the numerator and you FOILed the denominator. And so when you do that, you should get 14 plus 35i for the outer terms, 8i for the inner terms, and 20i squared for the last term for the numerator. The denominator, we would get 4 plus 10i for the outer term, minus 10i for the inner term, and negative 25i squared for the last term. Hopefully in that denominator you see that the 10i's are going to cancel out. That's a good thing. That's what should happen every time we use conjugates. In the numerator, I combine like terms, the 35i and the 8i, to get 43i, and then the plus 20i squared turned into negative 20 because of that I squared. The denominator, we had 4 minus 25i squared, so because of that I squared, the 25 became positive. So when we combine like terms, we get this. Now, in the homework in my math lab, I think they're going to want you to write your answer as standard form, which is the a plus bi form. So they're going to ask you to separate the numerator and the separate the terms in the numerators. And we'll get negative 6 over 29 plus 43 over 29i. And of course, if either of those fractions reduced, go ahead and do that before you put your final answer in to the homework questions. Okay, this first question, we've got the square root of negative 16 times the square root of negative 9. And so it's tempting to just say, well, let's multiply the negative 16 and the negative 9. But the problem is we can't multiply radicals together if there's a negative under the radical. So we have to handle that first. So I'm going to rewrite the first term as I times the square root of 16, which would be 4i, and the second term as I times the square root of 9, which would be 3i. So we have to take care of the negatives first. Now multiply those two things together, and we get 12i squared, which leaves us with negative 12. In the next term, or the next question, 18 and 8 are not perfect squares, so let's go ahead and take the negatives out of the radicals first by writing i's in front of them. And then let's simplify the square root of 18 and the square root of 8. So the square root of 18 we can simplify using 9 and 2. And the square root of 8 we can simplify using 4 and 2. So the first term gives us 3i, because of the I we pulled out, so 3 from the square root of 9, 3i radical 2. The second term gives us 2i radical 2 because of the square root of 4. And now that they're like terms, we can combine them. So if we have 3i radical 2 and we take away 2i radical 2, how many I radical 2's do we have? And it's just 1 I radical 2. Okay, this question's asking us to square this binomial. So I'm going to write it twice. Remember, anytime you have a square of a binomial, you want to write it twice so that you can apply FOIL. And then before we actually FOIL, just like in the last example, we need to get the negatives out from under the radicals where the 5's are. So I'm going to write those two radicals as I times the square root of 5. And now FOIL what you have here. And so we get 1 for the first term, negative I radical 5 for the outer term, negative I radical 5 for the inner term, and then positive I squared times radical 25 for the last term. So the two middle terms are alike, so we're going to combine those. The I squared is negative 1. Of course, square root of 25 is 5, so that last term turns into just negative 5. And then combine like terms at the end, and we get negative 4 minus 2i radical 5. Okay, last example. So we've got negative 25 plus the square root of negative 50 all over 15, and we want to simplify this. So I'm going to start by separating them so I can look at each fraction on its own if anything can be reduced. And notice I put the I in front of the square root of 50. Now let's simplify the square root of 50 kind of off to the side. That would be the square root of 25 times the square root of 2. So that leaves us 5 times the square root of 2 times the I that we had. Now reduce each fraction. Each fraction can get divided by 5. So the 25 and the 15 can reduce. The 5 and the 15 can reduce. And that leaves me with negative 5 over 3 plus 1/3 I times the square root of 2.